Welcome to today's Explainer. So today we're diving into a really specific, highly technical blueprint. We're going to walk through a step-by-step guide on how to build what's known as a God-tier, anti-cheat resistant Level 4 firmware. Specifically, we'll see how this methodical process takes a standard Enigma X1 board, which is basically a piece of raw FPGA hardware, and completely masks it so it looks and acts exactly like an Intel AX200 Wi-Fi card. It's honestly a fascinating look right into the depths of hardware emulation. All right, let's break down our agenda. We'll start with our main goal, move into Phase 1 for basic preparations, hit Phase 2 for hardware configuration, then simplify some really complex code, and finally wrap up with compilation and final verification. So, Section 1. What is the actual goal of this highly technical procedure? While the ultimate goal here is Level 4 firmware. According to the research repository we're looking at, this means transforming a raw PCI Leach FPGA clone into a fully emulated piece of hardware. The idea is to make it so robust and so perfectly disguised that it completely bypasses modern anti-cheat systems. It's not just about changing a name on a screen, it's about fundamentally changing the actual behavior of the hardware. When a security system interrogates it, our FPGA needs to respond exactly like a genuine Intel AX200 Wi-Fi card would. No exceptions. Okay, let's move right into Phase 1, basic preparations. This is where we gather our raw materials and lay the foundation for the firmware.
Step 1 demands absolute precision with your files. First, you've got to clone the official PCI Leach-FPGA repository. Then, you locate the specific project folder for your board, in our case, the Enigma-X1. Now, the crucial part here is to meticulously place all your custom scripts and Verilog files directly into a working directory right next to that project folder. Seriously, strict organization here is the foundation for literally everything else we're about to do. Moving to Step 2, this is where we achieve what's called Level 2 emulation. We use a specific Python command to completely clone the exact PCIe configuration space of a real AX200 card. The tool basically takes a data dump, either from a live card or a text file, and spits out configuration files. We then use these to overwrite the default files in our Vivado project. So we're essentially just copy-pasting the exact digital blueprint from our donor Wi-Fi card.
All right, with the files in place, let's transition into Phase 2, hardware configuration. This is where we start fundamentally altering the Enigma X1's identity. Here, in Step 3, we perform Level 1 emulation by manually patching the basic identity values in the core code. These hex values, they are absolutely crucial. We change the vendor ID to 8086, the device ID to 2723, and the revision ID to 1A. But even more importantly, the class code is set to 028000. By hard-coding these exact numbers, we're dictating that the system will exclusively recognize this hardware as a network controller. We're basically giving our FPGA its new fake ID. Skipping slightly ahead in the documentation to Step 7, we find that the hardware itself has to be set up to expect this new configuration. Inside Vivado, the IP settings have to match perfectly. The base address register, or bar 0, is set to 16 KB, memory 32-bit, non-prefetchable. Interrupts need to enable MSIX with a vector count of 17, and the link speed has to be Gen 2 by X1 to match the AX200. This ensures the physical hardware strictly conforms to the God-tier configuration we're building. Now we're onto Section 4, and this is what's really interesting, simplifying the complex code. We're going to decode the Verilog modifications in Steps 4, 5, and 6, because this is where the real emulation magic actually happens. Step 4 introduces DSN randomization. You can think of this as giving your hardware a dynamic identity. See, anti-cheat systems like Vanguard or ACE often look for static hardware signatures to hand out HWID bands. To get around this, we bring a script called DSN_randomizer into the project. It replaces the hard-coded serial number with a dynamic one that constantly shifts, making the card virtually impossible to track via a static signature. Pretty clever, right? In Step 5, we run into a fascinating physical problem. Modern anti-cheats don't just look at names, they actually measure hardware response times. A raw FPGA processes signals with superhuman speed. We're talking under 100 nanoseconds. It's kind of like the system is interrogating a hyperactive squirrel on energy drinks. But a real AX200 Wi-Fi card, that takes around 500 nanoseconds. That massive speed difference is a glaring red flag that instantly exposes an unmodified FPGA. So, how does the blueprint solve this? Well, through TLP timing jitter.
We route the signals through a new script which acts as an intentional bottleneck. It artificially delays the signal transmission by about 500 nanoseconds. It's basically like adding an artificial human reaction time to the processor's speed, which perfectly mimics the slower, authentic rhythm of a real AX200 card.
Step 6 is the final and maybe the most crucial code modification, Level 4 bar emulation. Right out of the box, our FPGA uses a default memory setup, usually just filled with placeholder data or zeroed-out memory. The guide instructs us to rip out that default module entirely and replace it with a modified God-tier script. Now, this isn't just static data. It's a dynamic state machine that flawlessly emulates exactly how a real network card behaves when it boots up. And that brings us to Section 5, the final phase of our blueprint, systematically verifying our methodical work and actually compiling the firmware. Step 8 requires extremely strict verification. Before you even think about hitting compile, you absolutely must run a specific self-check script in your terminal. This script scans through your entire project directory just to make sure you haven't missed a single one of those level 4 requirements we just went over. And the critical takeaway here is the result of that test. You cannot, and really should not, proceed unless the terminal explicitly gives you the grade of L4 full EMU. If it says exactly that, you're golden. But if it says literally anything else, it means your disguise has a flaw, and the anti-cheat system will almost certainly spot your hardware. Once you've verified that perfect grade, the final execution is pretty straightforward. You generate the bit stream in Vivado and wait for that complex synthesis to finish up. Then, you navigate into your implementation folders to extract your newly created .bin file. Finally, using tools like OpenOCD or a JTAG hardware manager, you flash that file directly to your Enigma X1 board. Just like that, the raw FPGA is completely transformed. This whole process brilliantly illustrates an ongoing cat-and-mouse game. We've just walked through an extremely sophisticated method to make an FPGA physically and behaviorally indistinguishable from a standard network card. And it really leaves us with a provocative question. As this kind of level 4 hardware emulation becomes more accessible and perfectly disguised, how will anti-cheat developers possibly adapt their strategies to detect them in the future? Thanks for joining us for today's explainer, and we'll catch you next time.